again. So this part we already finished, right? This is over, correct?
Yes, sir.
Okay. So we learned how to write the expression for the thermal resistance due to conduction in case of hollow sphere. So we say this is RT conduction in case of sphere, right? So the same expression can be written like this. In few books you will find they used to write this expression as this R2 minus R1 divided by 4 pi k R1 R2, or you can just solve this bracket and rewrite the expression like this. You can write R2 minus R1 divided by 4 pi k R1 R2. So this is somewhat easy to remember. That's why people do this. Otherwise, even if you write the expression as it is, equation 4, that's fine. Okay. So we know how to find out the heat conduction in case of a hollow sphere in the radial direction using the expression 4 pi k this temperature difference delta T divided by this bracket 1 upon R1 minus 1 upon R2, or you can write the expression using this kind of term here. So it will be simply this T1 minus T2 divided by this R conduction. So 4 pi k R1 R2 will go in the numerator, and what remains in the denominator is only R2 minus R1. Correct? So remember, this is the variable separable kind of method, and it should be applied only when you do not have the heat this internal heat generation term. I hope you know this. It should be used only when we do not have the heat conduction this internal heat generation term. Now it is time to solve numerical based on this hollow sphere. So take down this numerical 3.4 spherical vessel of ID 0.3 meter and thickness of 20 mm is made of steel, made up of steel with conductivity of 40 watt per meter K. The vessel is insulated with two layers, 60 mm thickness of conductivity 0.05 watt per meter K, and the second layer 0.15 watt per meter K. So the inside surface is at minus 196 degrees C. The outside is exposed to air at 30 degrees C with the convection coefficient on outside 35 watt per meter square K. Now there is a contact resistance of 1 into 10 raised to minus 3 meter square Kelvin per watt between the two insulations. So remember the ideal way how the contact resistance is specified is contact resistance is always specified on per unit area basis. Per unit area basis. So when I write this per unit area basis, it means in general we write the thermal resistance in the units of Kelvin per watt, or we know the unit of thermal resistance is Kelvin per watt. But you will find the unit which is given for the contact resistance is meter square Kelvin per watt. So this indicates this value is given on per unit area basis, means per 1 meter square of area. So if you divide this by meter square, you will get the same unit. So this thing you should remember, that the contact resistance is specified on per meter square basis. Is it clear? Then, is it clear how the contact resistance is specified? Hello.
Yes, sir.
How much time you are taking to respond? Are you really attending the lecture, or so this will be specified on per meter square basis, contact resistance. Remember this. Then determine the heat gain, the surface temperatures, and the overall heat transfer coefficient. So you have to find out the heat gain, then the surface temperatures, and the overall heat transfer coefficient based on outside surface area of the metallic vessel. So try to draw the diagram like this. I'm just showing the radius and nothing else. This is a hollow sphere. So this is your innermost layer, where the innermost surface is at temperature of minus 196 degrees C. So this must be some cryogenic fluid inside this cylinder, right? Inside this sphere, right? So this is your inner surface having the temperature 196 minus 196 degrees C. Then this is your thickness of your metallic vessel. This is the thickness, and the K of the thickness is 40 watt per meter K. Then you have two layers of insulation. This is the insulation layer 1, and this is layer 2, and their thermal conductivities are specified here. So first layer is having thermal conductivity 0.05, and the second having 0.15, right? And all their derived from the center, they are specified here. So the vessel is of 0.15 inner diameter, and the outer diameter of the 0.15 meter radius, and the outer radius of the vessel is 0.17 meter. Then if you add first layer, the radius goes to 0.23 meter, and if you add one more layer, then the total radius is 0.29 meter. So this is how the dimensions you should be specified. And on the outside, this is your T infinity temperature. The air is at 30 degrees C, and the heat transfer coefficient is 35 watt per meter square K, right? So this is what the given data, and you have been asked to find out what is the heat gain. So when I say heat gain, see, as per our convention, the heat transfer is taking in radially outward direction, right? But in this case, you will find that the outside temperature is more than the inner temperature. So the heat direction of heat transfer will be towards the center. Get me or not? So, but it doesn't mean that we should change our sign convention for doing this. Only thing is, when you calculate the value of Q, you will get the negative sign. So maybe suppose if you take get minus 100 watt Q, then this minus sign indicates that the heat is transferred from outside to inside. That's the only difference. Otherwise, you keep your convention as it is, that is from inside to that is R is positive in outward direction. So you keep that sign convention as it is. Fine. And
Yes, sir.
and one more thing which is mentioned here is this one. So there is a contact resistance of 1 into 10 raised to minus 3 meter square per Kelvin between the two insulations. Now, this is your insulation 1 and insulation 2, and in between there is a contact resistance. So this layer will give some kind of contact resistance, this one, correct? So that's why you will see there are two notations used here, right? Two notations are used for temperature. So let us say this is, if this is T1, this is T2, then the T3 is the interface temperature, then T4 is again the interface temperature, and 4 dash will give you the temperature considering this contact resistance. So there will be drop in temperature at contact. That temperature drop will be this T4 minus T4 dash. Get me or not? Is it clear?
Yes, sir.
Okay, fine. So find out this heat gain or the rate of heat transfer, and once you know the rate of heat transfer, then you can find out rest of the things. This problem is similar to what we did in case of hollow cylinder or the composite cylinder. Nothing big in this. You should be in position to solve. Only one equation is required to solve this, and that equation is Q is equal to delta T overall divided by R total. So this is the only equation you need to solve. So again, I would suggest you calculate the resistances separately. Don't put all the resistances at a time in the denominator of this expression. So use the notations like maybe call this as R conduction 1 or R1, then this R2, we call this as R3, right? And then you have the convection on this side. So this can be called as R convection. And apart from that, there is one contact resistance at this phase. So you call it as R contact. right? So you have 5 resistances in series now. 5 resistances in series, R1, R2, R3, the conduction resistance, then the contact resistance, and one convection resistance. So you know how to find out the conduction resistance in case of sphere. How you do that? So what is R1? The conduction resistance of the first layer for this hollow sphere. So what is the expression for this? So 1 upon 4 pi K1 into bracket. Bolo.
1 upon R1 minus 1 upon R2.
Correct. So similarly, you can find out R2, R3. So it will be 1 upon 4 pi K2, 1 upon R2 minus 1 upon R3, right? And for R3, it will be 1 upon 4 pi K3, 1 upon this R3 minus 1 upon R4, right? So this is how we will find out R1, R2, R3, 3 resistances. And then you have this contact resistance. So R contact, this value is already given. 1 into 10 raised to minus 3, right? But as I said, this is given on per meter square basis. So what is the area at this phase? So that will be calculated based on which radius? This radius. Correct? Get me or not? Hello. So based on this radius.
R4 पे से हम लोग कैलकुलेट करेंगे ना हम लोग एरिया.
Why? Where is interface? Where is contact between two insulations? It is at this radius, na? Or not?
Yes, sir.
So that radius you have to take into account, no? 0.23. So the area, you have to divide this value by area. Then you will get the resistance in Kelvin per watt. Remember this, huh? So this 1 into 10 is to minus 3 units I am writing here. Meter square Kelvin per watt, and you have to divide this by the area meter square. Then this will get converted to Kelvin per watt, right? Kelvin per watt. So divide this by area at this radius, which will be what is the area of the sphere? 4 pi R3 square. Now this is R1, R2, R3, R4, right? So it will be based on this radius. Is it clear?
Yes, sir.
So don't use this value as it is. You have to divide by area. Reason being, the contact resistance is in general specified on per meter square area basis or per unit area basis. So this is the only tricky part in this numerical. Find out the contact resistance in Kelvin per watt. Now all other resistances are in Kelvin per watt by default. Find out the R convection resistance. So what will be R convection resistance? It will be 1 upon this H, 1 upon H into area based on this radius now, outer radius. So this area will be 4 pi R4 square, right? So find out all those resistances and tell me now once you know the total resistance, all the resistances, find out R total. And R total you can use here, and delta T overall is, I will write the delta T overall or the temperature difference using our sign convention. It will be inner temperature minus outer temperature. So keep the sign as it is. So delta T will be written as minus 196 minus 30. This is your temperature difference, and whole divided by your R total, whatever value you get. So that should give you the rate of heat transfer Q. Clear? Hello.
Yes, sir.
Okay, fine. Then solve this. I'll be back in 1 minute. Just solve this. Okay, tell me what is R total you are getting now?
2.947.
So R total is 2.947 Kelvin per watt, right? And find out Q. What is Q now? It is minus. See, it is minus 326 divided by this number 2.947.
Minus 76.
Minus 76.69.
Okay, minus 76.69 watt, right? Okay. So once you know Q, then you know how to find out the interface temperatures, correct? We have done this before. How to find out the interface temperatures? This part. Or surface temperatures. How will do this? So Q is known to you. You will consider only this part of the your assembly, and what you can write is this Q. Q is constant under steady state. So Q will be delta T for this much thickness. So it will be this temperature T3 minus temperature T1, right? Correct? Or you can write temperature T1 minus T3 also. It doesn't make any difference if you are using the minus sign here. So if you are not using that minus sign, then you can change it accordingly. So you can use it for this. So as we are writing this temperature minus this, keep it T1 minus T3. So minus sign you can use here, and then divided by the R of this thickness only. So it is R1, correct? So Q is known, R1 is known, T1 is known. You can find out T3, right? So similarly, use the same expression for this layer, then the same expression at contact resistance. So at contact resistance, you will write it like this: T4 minus T4 dash divided by R contact, right? And you can find out the this temperature T4 dash. T4 will be known from this layer. Are you getting my point or not? Hello.
Yes, sir.
Yes.
And how to find out the overall heat transfer coefficient? You know this. Q is UA delta T. You can write it like this, right? And they have asked you to find out the heat transfer coefficient, overall heat transfer coefficient based on outside surface area of the metallic vessel. So this is your metallic vessel whose outside surface area is based on this radius, right? This one, outer surface of the vessel, correct? So you have to take this area pi R2 square, and the temperature difference is overall temperature difference. Your 196 minus 30 degrees C, and Q is known to you. So this is how we will find out the overall heat transfer coefficient U. Clear? You can cross check all the temperatures, surface temperature, interface temperatures, and the overall heat transfer coefficient. Your Q value is already correct, 76.6. You are getting 76.6, and that's fine. So solve it quickly and tell me whether your temperatures are matching with the answer which is given on the screen. So you calculated T3?
Yes, sir. Sir, I am getting minus 196.11.
196.11.
11.
Okay. Is there any student who is getting this value minus 195.88?
Yes, sir. Minus 195.88.
Abhishek, check your calculation. They are getting it correct. Okay, find out T4.
Yes, sir. Same answer.
T4 also is correct? Okay,
Yes,
fine.
sir.
So find out T4 dash. So T4 minus T4 dash will be the temperature drop at the interface, right? So this temperature drop divided by the contact resistance of at this interface. So use this value, Kelvin per watt wala value, not the 1 into 10 raised to minus 3. Otherwise it will be wrong again. So I think this was 1.5 into 10 raised to minus 3, something like that, right? Our contact resistance. And check this T4 dash. Now, as the contact resistance value is very small, you will see again the very small difference in temperature at the interface. So T4 minus T4 dash will be very small.
Hello, sir. Sir. Sir, in the expression that you have written Q equal to T1 minus T3 by R1, in that we have to take T1 as positive or what?
What? Repeat.
I mean, sir, in that expression, sir, T1 minus T3 by R1, sir, on the right hand side. So there we have to take the value of T1 as 196 positive or what?
See, if you are using Q value as minus, keep it as it is.
Yes, sir, I got it. Yes, sir, I got it.
Follow the sign convention only. Don't get into get confused unnecessarily. Follow the sign convention. So is it correct? T4 dash minus 8.64 degrees C. Hello. Is the value of T4 dash
Yes,
correct?
sir,
Okay, fine. Now
sir,
find out
value अलग आ रहा है.
T2 ka.
U, sir.
U. Okay. So what is the value you are getting?
0.32.
Point
32.
32 you are getting. Okay, you have used this area at this radius, right? This radius, no?
No,
So
sir. मैंने outside का ले लिया 0.29.
This one you have taken. Okay.
Yes. Okay.
So base this overall heat transfer coefficient area on outer surface of the vessel. This one.
Okay, sir.
And then cross check.
So 0.9454.
That's fine. It's close to the value which is given, no? Now T2 value is correct, 29.93.
Yes, sir.
So what we learned up till now is how to analyze the situation for a plane slab, hollow cylinder, hollow sphere. Then how to analyze the case of composite slab, composite cylinder, and composite sphere. how to find out the rate of heat transfer, how to find out the overall heat transfer coefficient, and how to find out the interface temperatures, right? All that stuff we have finished. So whatever numericals we have covered, so this number is 3.4 now. So these 4 numericals are more than sufficient to solve any kind of problem for these 3 standard cases. Any kind of problem. You take any book, you should be in position to solve the numerical if you have understood these 4, provided you have understood the 4 problems. Clear? Now shall I go ahead?
Sir, can you write the formula for U, sir? I mean the area that we have to take. R3 के respect में लेना सर ना?
See, I have already written here, so you can use this, right? So area, this
So that
area
four.
is based on this radius. This radius.
Yes, sir.
And you can use this formula that U naught A naught means the product of the overall heat transfer coefficient based on outer area and the outer area. This must be equal to the overall heat transfer coefficient based on inner area into the inner area of your sphere. So this is valid. We have seen this before, right? So either you calculate UI based on inner area and then calculate U naught, or reverse also you can do, one and the same. But you should take the corresponding area, otherwise it will be wrong. Fine?
Yes.
Okay. Now moving further, we'll talk about the systems, radial systems basically, and we'll try to find out is there anything like the optimum insulation thickness for that kind of systems, hollow cylinder or a sphere, radial systems basically. So existence of an optimum insulation thickness for radial systems. We'll try to answer this question. Is it possible? Now look at this diagram. You should draw this diagram along with me. So I am taking the cylindrical kind of a system. Then I have the inner radius Ri and the outer radius. I am taking the outer radius as R. Then on outside this there is a temperature of the fluid T infinity, and the heat transfer coefficient is small h outside the surface. And this thickness is nothing but the insulation thickness having thermal conductivity K. And the inner surface temperature is Ti here, right? Clear? So draw this diagram, and corresponding thermal circuit also is shown here. Now consider this as a cylinder, right? Cylinder, and this Q dash indicates, see, Q is the rate of heat transfer, and if I divide this by length of the cylinder, then I am going to use symbol Q dash to represent this Q. So you can call this as a heat transfer per unit length. Clear? Note down, Q dash is heat transfer per unit length. So if I am writing this part as a Q dash, then this you can call as a R dash. So this is R dash thermal resistance, and this can be called as R dash convection resistance, right? So if you are not comfortable with this symbol, you can change it accordingly. So right here Q, then you have to add L here. So we know how to find out the contact this thermal resistance in case of cylinder. So we know it is written as ln R2 by R1 divided by 2 pi k L, right? So we used to write R thermal resistance of conduction for cylinder. This is written as ln R2 by R1 divided by 2 pi k L, right? So I am writing this R dash because I am taking this L on the left hand side. Or if you are getting confused, simply write L here, and then this will be RT only, and L here,
Sir,
and this will be.
Sir, in this
I will
case,
write.
heat is coming inside, na?
Okay.
Okay.
So that's why the symbol is shown here. So ln r by ri divided by this sign convention doesn't make any difference right now. So ln this r by ri divided by 2 pi kl for this, and this should be written as 1 upon 2 pi rl or into h. So this is 1 upon ha basically, 1 upon ha, and then use symbol only q to represent the rate of heat transfer q through the cylinder instead of q dash if you are getting confused, right? So you can write this expression that q dash is T infinity minus Ti divided by r dash total, or if you are using q alone, then write q is equal to T infinity minus Ti divided by r total. So either of this equation is fine. As length is common, you are taking it on the left hand side and nothing else. That's why q dash they are written. Now we are going to ask this question. So an optimum insulation thickness would be associated with the value of r, means this radius r, that minimized q dash or maximized r dash total. So if you are using q symbol, you will say that minimized q or maximized r total, right? So that thickness of insulation will be called as the optimum thickness of insulation or optimum insulation thickness. I hope you understood this statement. What we mean by optimum thickness of insulation. So what should be happening is, if the thickness is optimum, then that will maximize the total resistance R total and will minimize the rate of heat transfer Q. Correct? Now to check this, what you have to do is you have to differentiate this R dash total or R total in that case with respect to R, equate it to 0, right? So differentiate R dash total or R total with respect to R, equate it to 0, and then solve it further. So R total is what? R total is ln R2 by R1, this R by Ri divided by 2 pi KL, right? Plus this 1 upon 2 pi RLH. This R total is sum of these two, no? So we have to differentiate this with respect to R and equate it to 0. So if you do that, you will get this term, and after solving this, you will get this expression that R will be represented as K by H. So this radius R will be equal to the ratio of thermal conductivity to the heat transfer coefficient H. To do all these mathematical steps in between, I have not written it on screen. I will leave it to you to find out. It's very simple. I hope you know this. Correct? So why the derivative of this term can be written like this? I hope you know this.
Yes, sir.
Okay, fine. So once you solve this, you will get R is equal to K by H. Now we have to check whether this R will give optimum thickness or not. So to determine whether this R result, means this value, maximizes or minimizes the total resistance, we want to maximize it for optimum radius. So we are checking whether it maximizes or minimizes the total resistance. We must evaluate the second derivative. So we have to find out the second derivative of this. So I am taking the second derivative now. So d square r dash total to dr square or d square r total by dr square, whatever your term you are using, use it. So you have to differentiate this again one more time. So you will get this term minus 1 upon 2 pi k r square plus differentiate once more. So you will get 1 upon pi r3 pi r cube h, right? And evaluate this term or the second derivative using this value of r, k by h. So put r equal to k by h in this expression and find out what you get. So this is this mathematical simplification. So what you get is this term 1 upon 2 pi k cube divided by h square. So all these values are positive, k, h, right? Pi is 3.14 we know. It means this whole term will be greater than 0. This is what we have proved. So the second derivative of the total resistance is greater than 0. So what is the significance of that? Second derivative is greater than 0. So the significance or the meaning is that R is equal to K by H is the insulation radius for which the total resistance is minimum. So instead of maximizing the total resistance, what is happening is it is minimizing the total resistance, right? So initially we thought that optimum radius should maximize the R total, but it is not doing that. So if this value would have been negative, our previous assumption would have been correct, that R total is maximized, but it is not happening. So R is equal to K by H is the insulation radius for which the total resistance is a minimum and not a maximum. So hence we conclude that the optimum insulation thickness does not exist. So there is nothing like optimum thickness of insulation. So what was the initial condition for the optimum thickness of insulation? It should minimize Q dash and maximize R total, correct? So this value R equal to K by H, instead of calling it as optimum insulation thickness or optimum thickness of insulation, we will use some different terminology. And what is that terminology is given in the next slide. So should I go to next slide now?
Yes, sir.
Okay, fine. So remember, there is nothing like optimum insulation thickness, huh? Okay, and now we will replace that term optimum thickness of insulation by the term called as a critical radius of insulation or critical thickness of insulation. Now the same diagram is shown here, and so we will conclude based on the previous slide that it makes more sense to think in terms of critical insulation instead of optimum insulation. So that's why that term K by H is nothing but the critical thickness of insulation. So this RCR, or you can simply write RC, the critical thickness of radius of insulation, is given as K by H. Now this is true for the cylinder. We are talking about cylinder, right? So RC, critical radius of insulation, is K by H in case of cylinder. Clear?
Sir, do we have to
bolo.
prove this R is equal to K by H?
You have to prove this. No, we proved it using the resistances. No, these two resistances,
Yes.
conduction as well as convection. Now there is one graph. You should understand this graph. I'm going to ask questions even in oral also. So look at this plot now. So what you can read on the vertical axis. So here it is R dash T, right? So that's why unit is given meter Kelvin per watt, because this is per meter length. So if you want to just plot RT on this vertical axis, then the unit will be Kelvin per watt, correct? So you can plot RT also. Is it clear? Now what is there on the horizontal axis? This R minus Ri, R minus Ri, right? Ri is the inner radius and R is the any radius which you choose here. You go on adding the thickness, your R will change, no? So this is how the difference is plotted here, R minus Ri. So when you are at the inner phase, R and Ri are equal. That's why you are starting from 0 here. Correct?
Yes.
Okay, fine. So what you conclude from the graph is, see, this is your conduction resistance, right? I am writing L here. So call this as R only and not R dash. And this is your convection resistance. So if you are plotting RT, I will call this as only R convection, this as R conduction, and this is R total, not dash. Fine. So let us talk in this terminology only. So if you try to plot the R conduction along the this increase in the thickness of insulation, So what you are trying to do is you are trying to find out what happens to the resistance if you go on adding the thickness of to the insulation, thickness of insulation. If you go on adding the insulation, what will happen to the conduction resistance? So what is happening is clear from this graph. What is happening? Sorry, this is for convection. This one, conduction. What is happening?
Sir, conduction graph sir parabola hai na?
See this one, this curve, second curve. See, if you go on increasing the thickness of insulation, what is happening is your resistance is increasing, na? Conduction resistance is increasing, right? Hear me or not? Hello?
Yes, sir. Yes,
See,
sir.
you are plotting this term simply. You are plotting this term. See, 2 pi KL will be constant. So ln R by Ri. So it means Ri is also constant. So your term R conduction is varying with R. You go on increasing the R, this term will increase. This is how the conduction resistance is increasing. Correct? And
So you want to say that Ri is fixed, na?
Huh? Ri is fixed.
Ri
No?
is fixed. Yeah, yes. Or
This
no?
is fixed. No? So if you increase R, this term will increase, right? So that's why conduction resistance will increase. Now look at this term, convection resistance.
Sir, one doubt, sir.
If you increase R, बोलो.
सर वो कंडक्शन का जो सर ग्राफ है ना मतलब वो सर जीरो से क्यों पास हो रहा है बिकॉज मतलब लॉगरिथमिक ग्राफ सर जीरो से पास नहीं होता ना कभी तो ये डाउट है मतलब आर और आर आई इक्वल हो सकता है क्या ऐसा पूछ रहा हूँ
See, this R will become 0, na? I see, if R is equal to Ri, this will be ln 1, na? So what is ln 1?
0 sir.
Then from where it should start?
Yes sir, from 0.
So if you look at second term, convection resistance, with increase in R, keeping this 2 pi h and L constant, with increase in R, this denominator will increase. If denominator increases, your whole term will decrease or not.
Yes sir, ये graph clear है sir, convection का clear है.
That's why this curve is a dropping curve. So with increase in thickness of insulation, convective resistance decreases, and with increase in thickness of insulation, conductive resistance increases, right? But
Yes,
we are interested in R total and not in individual resistances. So what you have to plot is R total now. So look at R total. This is your R total. So what happens is, initially when you start from your base radius, if you go on increasing the thickness of insulation, your resistance will go on decreasing like this. It will become minimum at this point. Resistance will become minimum at this point. And if you go on adding further the insulation thickness, the resistance will go on increasing again. So this is the point where R is minimum. So if you use this expression delta T by R, right? So keeping this as a constant. So if you get R as R minimum, then this Q must be maximum or not?
Yes sir, inversely proportional.
So the radius at which this thing happens, we'll call it as a critical radius. So if your radius is more than the critical radius, what happens will be seen through this graph for the resistance, and if it is less than the critical radius, what happens to the heat transfer will be seen through this graph, right? So in next slide I will show you how Q is plotted. So just go through this line, last one. So critical insulation radius which maximizes heat transfer, that is below which this Q dash increases or Q increases with increasing R, and above which Q dash or Q decreases with increasing R. So that point is nothing but the critical radius. I already talked about this radius. Clear? Now in next slide I will show you how Q is plotted, and you have to connect that Q to this graph. Hello. Shall I go ahead?
Yes, sir.
Okay. So this is for cylinder. Huh? Now we'll talk about sphere. So take down quickly. So this is for sphere. The same technique is used. Nothing big in this. So the radius, inner radius is R1, temperature is T1, outer radius is R2, temperature is T2. And then we have the sphere and the insulation, right? And outside heat transfer coefficient H and the temperature of the surrounding fluid T infinity. And then you can plot similar kind of the diagram equivalent to the previous case. And then I am writing R conduction, R convection. So we know how to find out the R conduction, R convection, right? Correct? So this is your R total, which is sum of conduction resistance plus convection resistance. So you can simplify this term like this. And then you have to differentiate this with respect to differentiate R total with respect to R. Write this equation, equate it to 0, and then you will get this expression that the radius R2, previously we used R symbol, here it is R2. So R2 will be 2K by H. So instead of K by H, now you are getting 2K by H for sphere. This additional 2 is there in case of sphere. So this is nothing but your critical radius of insulation. Now using this radius, again we are checking for the second derivative, and this time also you will find that the second derivative value is more than 0. It means R dash is not maximized, right? R dash is not, or R is not maximized, correct? So it means in this case also we are not going to talk about the optimum radius of insulation, rather we will call it as a critical radius of insulation. That's why this term is defined as the critical radius of insulation, R critical 2K by H. Clear? Clear?
Yes, sir.
Same logic is applied, nothing else. Same logic as that of cylinder. So remember, for the cylinder, the critical radius is K by H, and for sphere it is 2K by H, right? So what is the time? Still we have 10 minutes. Huh?
Yes.
At least we'll discuss this numerical. You can solve it on your own. It's a very simple numerical. Copper pipe carrying a refrigerant at minus 20 degrees centigrade is 10 mm in outer diameter and is exposed to convection at 50 watt per meter square K to air at 25 degrees C. It is proposed to apply insulation of conductivity 0.5 watt per meter K. Determine the thickness beyond which the heat gain will be reduced. Now calculate the heat gains for 2.5 mm, 5 mm and 7.5 mm thickness for 1 meter length of the pipe. The convection coefficient remains constant, so take H as constant. So how to solve this? So first of all, you will find the critical radius RC, which is K by H. Then you will use this expression Q equal to the delta T by R total, same expression. So you will find out Q, overall temperature difference, T1 minus T infinity divided by the sum of two resistances, conduction resistance plus convection resistance, right? And then you will find out what is Q of bare pipe. So when we say Q of bare pipe, means you need not have to consider the insulation, right? And then you'll find out what is the Q when you have the radius. This is your base radius plus 2.5 mm thickness. This is base radius plus 5 mm thickness, and QR with base radius plus 7.5 mm thickness. And then check whether you are getting these values or not. Hello.
Yes, sir.
Now find out. So again, it is worth noting down. See, the Q sign is minus, right? So that's why they call it as heat gain. Means heat is transferred from outside to the inside. So critical radius is k by h. So what is k?
0.5.
Huh?
0.5, sir.
0.5. And what is h?
50. We are getting the same answer.
So 0.01 meter you are getting, right?
Yes, sir.
Now remember, this K is of insulation, and not the K of copper pipe. Do you understand this or not?
Sorry, sir. Can you repeat that?
See, this K is thermal conductivity of insulation and not the thermal conductivity of copper pipe. I am going to confuse you in examination by giving a lot of values, unnecessary values.
Okay, sir. So you are saying that for copper it is like material property, na?
So find out what is K, that K is of insulation or K of material, you should understand while using.
Sir,
Hmm.
sir, we are for the thickness we are going on varying R2 now.
बराबर. See, this is your base radius, right? This is your base radius. So what you are doing is you are adding the thickness to this, no? Correct. So base radius will remain same, R, let us say. So what is varying is this R2. Now if I am using one layer, it is R2. Now if I add more thickness, again this R2 is increasing or not. R1 is same. R1 is base radius. Clear?
Yes, we are getting, sir. And sir, this 10 mm is length, na?
So where it is written, a copper pipe carrying refrigerant at minus 20 10 mm in OD, outside diameter. Means this is R, your base radius, or R1, whatever notation you are using is half of this, correct? 5 mm. Get me or not? This is diameter, not the radius. Hello.
Yes, sir. Getting, sir.
So just solve this at your end, and tomorrow you can maybe we have lecture tomorrow, no? You can tell me whether these values are matching or not, right? Now what
Yes.
I want to show out of this problem is in the next slide. See, I have plotted those resistances in Excel now. The same problem is solved using the Excel. So what you see on this axis is resistance, right? Resistance is plotted, and this is along the radius, right? Get me or not? This is along the radius. So you go on increasing the radius, what happens? Go on adding the insulation, what happens? So this blue color plot, this indicates which resistance? What happens if thickness of insulation increases? What happens to conduction resistance? What happens to convection resistance? With increase in R, the conduction resistance, increases. So
And
this curve is
convection
like
decreases.
this, and convection resistance decreases. So this must be convection resistance curve, right? And what is this green colored plot?
Total
This is
resistance.
total resistance, right? And what you can observe is, as we said before, that initially when you add the radius of when you add the insulation to the base radius, you will observe there is decrease in the total resistance, right? It will become minimum at certain point, and then it will again further increase, right? So the point where the total resistance is minimum, so let us say it will fall somewhere here, right? So don't you think this is nothing but your critical radius? Look at your value and look at the graph. It's one and the same, right? correct? Hello.
Yes, sir.
So if your base radius is, let us say, this is your critical radius. If your base radius is less than critical radius, and if you go on adding the insulation, means you are increasing this R. This is your base radius. You go on increasing the thickness. What happens is the heat transfer, the resistance will, total resistance will decrease first. So if total resistance decreases, it means the heat transfer increases, right? So that you can understand from this graph. So this is what Q plotted against this radius R2. So you will see that there is one point here which will give you the critical radius 0.01 and the corresponding value of Q. So this must be Q max, right? Because at this point resistance is minimum, right? So now from this plot you should understand this terminology. So this is your critical radius, and if your base radius is less than critical radius, means you are talking about this side. If your base radius is less than critical radius, and if you go on adding the insulation, what will happen is heat transfer will increase. So this indicates heat transfer will increase, correct? So how much heat transfer will increase? Up to what point heat transfer will increase? Up to the point until this R becomes equal to RC, right? Correct? And if you go on further increasing the thickness to the insulation, then your Q will decrease. So we are talking about this case. So if R is greater than RC, and your intention is to increase the heat transfer, then there is no point in putting the insulation thickness or increasing the insulation thickness. That's what you should conclude from this graph. Are you getting my point or not? So whether to add the insulation will depend on what you want to achieve. Whether you want to increase the heat transfer or you want to decrease the heat transfer, right? These two things, and this is direct connection with the base radius, right? Whether you want to increase Q, decrease Q, and what is your base radius. So these 3 points you have. So don't be under impression that in cylindrical system, if you go on adding the insulation, the heat transfer will decrease all the time. It is not going to happen. Remember this. Are you getting my point or not?
Yes.
So you may come across situations where you don't want heat transfer to take place. For example, if you have a steam flowing through a pipe, then you don't want that steam to lose heat to the surrounding, right? So that time you will put the insulation from the outside of your pipe, steam pipe, and your intention is to minimize the heat transfer to the surroundings, right? Same is true about the cryogenic fluid. So if you have the cryogenic fluid, let us say at minus 200 degrees C, stored in a vessel, let us say spherical vessel. So now your intention is to minimize the heat transfer from surrounding to this cryogenic fluid. So you are trying to minimize the heat transfer, correct? So if you come across any application where you want the heat to be dissipated as highly as possible, so there your intention or your purpose will be to maximize the heat transfer, because you don't want to increase the temperature, or don't want to see the increase in temperature of the material itself, right? Otherwise it will melt, no? Or burning may take place. So depending on your application and your intention, what you want to achieve, you have to compare whether Q should be increased, Q should be decreased, and this has to be directly compared with the base radius, right? So base radius will decide whether to add the insulation or not for that particular intended purpose, right? So I think we are running out of time. What is the time? 23. We should stop now. Just a minute.